This is Brian Putt. Today I'd like to talk to you about multiple objective decision analysis, looking at uncertainties where they are difficult to quantify. And you have maybe a number of stakeholders, and they all have different risk preferences. So how might we go about this? First of all, I'm going to describe the existing model that I have on the screen now, and then we're going to run a sensitivity to what's known as the weights that are assigned. So sometimes it's referred to ranking and weighting. So let's assume that we had 8 value measures, and we have identified through a framing process, a DQ framing process, several strategies. Let's say strategies 1 through 4. And then for each of these value measures, we would identify what was the best, strategy 1 here, and what was the worst, that would be strategy 3. And those get assigned a 100 and a 0, and then the other strategies get assigned values between those 2 points. So over here, we see value measure 3, strategy 1 has a 0, and strategy 4 has a 100. And so that's true for all of these. There's always a 0 and a 100, and then the others that are not assigned are given values. So now that we have values here, we need to understand how to weight these different value measures. What is most important to you? What is most important to me? That may be different things. So let's assume we have a number of people here, John, Mary, Rick, so forth. And so they would each assign weights to these value measures. What's most important to them? What's least important to them? And they have to add up to 100% for each person. I guess this one's adding up to 101. So that's a problem. We'd have to adjust that a little bit somehow. We'll make that a 9, okay? And then we're good. All right. Now in this particular case, what we did is we took the average of those, and that became the weight that we used over here on the unnormalized, and then we normalized it to 100%. In this case, there wasn't any normalization required because we required everyone to make them 100% to start with. But you know, you could do it slightly different if you wanted to. Anyway, the idea is they have to come to 100%, and then I can do a cross multiplication here, some product of these values times these weights, and I come up with a score. It's very deterministic, and then I can rank these. So in this case, this is the lowest rank, so it gets a 4. This is the highest, so it gets a 1. And then I can identify the best strategy, that is strategy 2. And the second best strategy, strategy 4. These are important because we're going to show how to do sensitivity now. All right? So, how are we going to do the sensitivity? First of all, let's make this a SIPMath model. So I'm going to come over here and go SIPMath initialize. We'll do 1,000 things. Reset number to 1,000. And it added this PM table and the SIPMath chart data. Now let's define some uniform distributions. So we'll go SIPMath generate input uniform. We'll just use the a seed that's assigned by SIPMath. So now we have some uniform numbers here. Let's take the sum of these. And then we'll normalize these right here. So it's going to be equal to that divided by the sum of 4. And I can copy that down. And now these normalized weights add up to 100%. And they are also probabilistic. If I come over here to trials, I can go to different trials and you'll see that they're all moving. Right? Now the way this model is set up, we can identify a method for calculating the values down here. Here's the average. Or I could do an individual. So here is Karen. So Karen had 10, 20, 10. If I get 10, 20, 10. So I could look at each person individually if they wanted to see what they looked like, what their risk preferences were. And so there may be differences between which one, each strategy that each person prefers. But now we have another method. We want to look at this probabilistically, saying, well, how important are the weights that are assigned over here? So let's assume that we want to, instead of the individual, we want to go to a Monte Carlo approach. Now, what is that going to do? Okay, Monte Carlo happens to be a number 1, so I'm going to change this here to refer to this S column. And then we should be able to copy that down. Oops, we got a 14 there. That doesn't look right. Why do I have a 14 there? Oh, because this should be a 0 by definition, because I don't have anything there. All right? So now I've got these weights. So now what happens? If I did that same trial thing, look at different trials, you'll see that these numbers are changing because I've got different weights associated with each of those trials. Close. Okay, so now let's do a few things here. First of all, let's define the best strategy as an output variable. Define outputs, and we'll call that best strategy. And we'll say yes. Output names should be the second best strategy. Yes. Okay. Now we can plot those. Well, actually, I can do it this way. I have a plot, and I'll do a cumulative over here. And then I can combine these. Control X, Control V, and we'll get the titles on here, legend. So the best strategy in 1,000 different trials of these weights, it's always strategy 2. It's always strategy 2 that is the best. The second best strategy is strategy 4. It's the best strategy like 30% of the time. And you can see that strategy 3 is not very often the best strategy. So there's something else we could do here. We could define these as variables as well. So we'll define those outputs. Output names. I can do multiple here at the same time. We'll call them strategy 1 to 4. Okay. And we can then do graphs of those as well. Let's do it right here. And then we'll combine those. Control X, Control V, Control X, Control V, Control X, Control V. And now we add the legend here. So what if we conclude from all this? Let's put these two charts together here. So clearly strategy 2 is the best. It's clearly the best over here. You come over here and you might argue that strategy 4 is always the second best, but that, if we see, is not the case. Strategy 4 is only the second best 30% of the time. So there are times when strategy 1 is actually better than strategy 4. Strangely enough, strategy 3, even though it's to the right of strategy, get the numbers here, 1, it's so similar to strategy 2, or strategy 4, that it's really very, very rarely better than strategy 4. But strategy 1 is more different. Anyway, so this is a way of doing sensitivity and help make a decision on which strategy to follow. Hope you found this helpful. You can contact me at brianputt@theputts.com. Thank you very much. Bye. If you'd like to learn more about SIP math, I suggest you visit probabilitymanagement.org. They have a wonderful website with all kinds of tools there, shown down here, who they are. You can download models, and there's tools down here to include the SIP math toolbar itself. You might also read The Flaw of Averages by Sam Savage. And please visit my YouTube channel. I have over 80 videos that cover a wide range of topics to include uses of the SIP math tools, how to use the icons, cost and schedule risk analysis, portfolio analysis, value of information, lots of videos on that, and some mind testers. Hope you enjoy. Thank you.